Yeah, today we have two presentations. One presentation from the openEO project, and then right after another presentation from the Candela project. Each of the presentations will take around 45 minutes plus 15 minutes of question, more or less. And we're going to start now with openEO. So let's get started here. So what is openEO? openEO is an API for standardized access to Earth observation data, and this project is led by the Technical University of Vienna and has a number of different partners, as you can see on this slide here. And the goal of openEO is, why do we need openEO? Basically, we have a lot of Earth observation data available now. We have different satellite missions, be it optical data from missions like Sentinel-2 or radar data from missions like Sentinel-1. And we do not have just individual images of these. We have different kind of products derived from this. We have a whole time series of this. And all we want to do is basically analysis made looking into trends in a time series, doing interferometric analysis based on radar data, or just do simple land cover mapping. Unfortunately, however, it's not as simple as this. In most cases, we have some kind of complex infrastructure, or a number of software layers, virtual environments, and so on in the background. And it's not easy for a simple user to get a hold of this, especially when you have to deal with a lot of data. The data itself, you can see maybe down here somewhere on some disks, and all our processing in the very end of a long chain of services, interfaces, and components is happening somewhere here for a researcher, maybe in a programming language like R or Python, or for a web developer, something like JavaScript. Typically, users are not even aware of all the complexity here nowadays. There are a lot of cloud services, let's say, who are structured in different ways. Some of them, for example, organize the data just based on file access, or the data is organized in some form of data cubes, or there's some more high-level API to do this. When I now develop my software, for example, I'm a developer working with R, then I have to write different interfaces of accessing the data if I want to access data in a data cube or on a file system or on another high-level API. Now, if I work in an institute and maybe people work with different programming languages, then I also need to write interfaces to all the three of this again, because for all languages this is different. So you can see from this that there are a lot of confusion of how to access data, and a lot of work just to get the interfaces right to all the different possibilities of where to connect. So the basic idea of openEO is to replace this connection part basically with an API, a RESTful API actually, and then all we need to do is develop clients that are conform to this, and backend drivers that are also conforming to this. So we kind of define a language in the middle that everybody can speak, and in this we reduce the complexity and the number of implementations quite drastically. This again also leaves us the possibility that we are not anymore locked to a specific vendor here, because now if we talk through this API and we do something, I don't know, on the Amazon cloud or on the Google Earth Engine, in theory, if both of them work with this API in the middle, then we as a client don't need to change our code. We just can change the endpoint. When doing so during the project right now, we discovered that a big work was not only to define the API, but also implement the client and backend implementations of this. That's here symbolized by the inverse of the sizes here of the workload. But the good thing is this has to be done basically only once per backend and per client. And this is also all available as open source from our project. So in order to get started with openEO, we have a lot of different guides how to do this. All of openEO is based on a RESTful API, so it's all going through HTTP calls, being at GET and POST, and is following the Open API specification version 3. If you want to develop own developments or look how it goes, you can first of all check out our GitHub, where you can find different implementations based on different backend technologies. For example, here from VITO, we have something that is based on GeoPySpark. We have a driver that is connecting to the Google Earth engine. There are other implementations like the one we do here in Eurac, which is based on OGC WCPS interfaces. And of course, if you want to develop your own stuff, you can use all of this and then adapt it to your own infrastructure needs. Or you can start from scratch. In this case, since we are based on Open API specification, you can also just use this to your advantage and use tools like code generators that provide you already some steps to implementation of this. And when you do start implementing something in openEO, then you should always start with the essential endpoints. So what is defined as endpoints in the RESTful API? Of course, you need to have some kind of discovery services in order to see what is available. This is the root slash in our case. You can get some information about versioning and output formats. These are all information about the service, what can be done there. Then, of course, discovery of data. This is done through collections, and for more detailed information about specific collection can be done with this extra here, collection ID. We have, of course, what can you do with the data? So this is processes. The basis for all computation in openEO are processes. The next thing is in openEO, you can chain processes through something which is a process graph. You can see this more clearly later in the live demo, but you can define in an abstract way how things should be processed, and this is done with process graphs. And of course, when you're done with your work, you want to somehow access your results. This can be done either synchronously or through a batch processing matter, where you then can create a job, submit it for processing, and in the end, when it's finished, download the results in asynchronous manner. This is especially if you have long-running jobs on big areas. Of course, once you have your system, you might also want to make sure you know who's logging in and what they can do. So there's authentication process there, which then can also be used for things like billing if you have specific plans in your infrastructure. There's something where people can upload their own files and handle their own files, which for some processes you might need to upload shape files in order to limit the area where something is processed or something like this, and then this can be done here. You can also provide your processing chain later as a web service, so that people can access the results of your processing directly through something like a WMS or XYZ or even a web coverage service. And you can also integrate into your processing chains user-defined functions. For now, we're developing this for R and Python, so that people can even execute their own arbitrary code to give the highest possibility of flexibility when designing processing workflows. In general, all the information that is exchanged between the clients and the backend is somehow encoded in JSON. On the left side, you see a quick overview of a descriptive document showing how Sentinel-2 time series is displayed. On the right side, you see the beginning of a process graph, which is also a nested graph of JSON objects, basically, which describes how processing is done. We have a lot of resources available online. Maybe for this, it's even better that I stop for a moment the presentation and switch to my browser to show you this directly. So we have our website here, openEO.org. There you get some overview of everything. Most of all, if you want to work with openEO, this is a software stack. So all the informations you can get here are are all bound together here. If you are coming from the user or client perspective, we have different guides of how to do this. So there's a getting started guide for users showing you what you can do. Then if you want to develop your own client libraries, there's a guide for development of client libraries. And if you're developing your own backend, there are different examples and guides of how to get started with your backend development, basically here. Most importantly, there's of course our GitHub. So we have our github.com/open-EO. This is our group. Here you can see all the different implementations. So really everything we do is open source. There are tens and more thousands of lines of code that you can find here in all kinds of different programming languages. Of course, for getting started, the center of everything is the API. As I said already before, we are releasing different versions all the time. We have gone through a number of iterations, and seeing here, now we have come to something more stable in the 0.4 version, and we hope that by the end of this year or beginning of next year, we're going to release our version 1. Then this project is already running since 2 years approximately. Exactly. The API itself is documented here and especially you can get the core API reference where you can really see how for all the different endpoints you have to implement your different HTTP methods with examples and so on, how you expect answers to requests to be done, what are the required parameters and so on, what kind of responses should you give on a successful request, or what kind of error message should you get if the request is wrong, basically. This was a bit of an overview of that. So we can go back to the presentation here. So the API reference. One thing exactly most importantly maybe is another big issue. Apart from defining the API of how to talk to each other, we also came up with a whole catalog of processes defining that you can call through the API in the different backends. In the end, this catalog is also available online. You can find the link here, but also over the different websites of openEO, basically. And here we have group processes to all kinds of different functions. I don't know, I think there are 140, 150 different defined processes right now. And all the different backends that are part of the project right now are working on implementing them in their infrastructures, basically. These different backends you can actually also find over a website, which is the hub.openeo.org. Here you see some of these that are available also for public testing. So you can look into these and see which version are they on right now, which functionality is available there, which data set and so on. So this hub site basically already uses these endpoints, which I showed you before for listing what you can do. Here you can see then, okay, here I have 53 of the processes available that I can use in my process graphs, basically. Exactly, and this is different for different ones. You can see the number of processes, collections, and what is done is different depending on the backend that you look into, basically. But the important thing is that all of them, the ones that are listed here, they are available for public testing also. Okay. We are now having these different backends that are showed here and client implementations available. So there's an implementation in R as a standalone desktop kind of server, which everybody could run even on their own computer. There are more advanced systems like the one from VITO running on their ProBV exploitation platform. But I think they have deployed now also the DS. Jeroen will tell you later about this more. There's a connecting driver to the Google Earth engine. Synergize is developing something on the Sentinel Hub. EODC is developing something. Mundialis has something based on Actinia, which is a web service interface to GraphJS basically. And then the JRC is working also on an implementation running on the GeoDPP. So there are all different application implementations there already. And on the client side, as I said, we have R, Python, and JavaScript for now. R and Python basically for researchers, and JavaScript for web developers in order to visualize results. We are hoping now to bring this also into the DSs. Maybe we can integrate this somehow in the ESA workflows. Some discussion has also been done with the European grid infrastructure people, and maybe also DLR. We do not yet, these are all question marks. We had some discussion with some people there, but none of them are confirmed, and I'm not speaking for them. So this is just something that could be, but is not confirmed in any way. Okay, this I've already shown you. Just maybe I can go in a little bit more detail here quickly on how this is done on Eurac. So this you saw before already, confusing infrastructure with a lot of components. This is what we have here. So we have our existing infrastructure. And in our case, we have a Rasterman Community Edition running here as a data cube hosted in this infrastructure, which in itself, again, exposes OGC services. In this case, through the Community Edition, you can have the WCPS for processing, and the web coverage service for data access, and the WMS for data visualization. And these we are interfacing now with openEO by developing intermediate web container web archive in Java, which exposes then all the API. This is developed also in Git. It's based on, I'm not sure if I should even go into detail here. Basically important is only that in order to run this, you basically just have to install these different components. This is a pure software stack, so there's no dependency on specific hardware. Here we have tested this, deploying it on CentOS 7 and Ubuntu. You need some kind of web container, for example, Tomcat, but it could also be more simple, something like Jetty. And then you should configure your environment for HTTPS in order to have encrypted transmission of all of your data. And finally, you just need a simple database like SQLite and GDAL for some image operations, and copy the file in here. And then you can just do some configuration based on what's your WCPS endpoint, so the IP address to your Rasterman server. Or if you have another WCPS implementation, you can use this also, since we are not directly linking this to Rasterman, and the URL of your openEO. And if you do authentication, then you should specify this. So there's just some things you have to configure, but just very few elements there to be done. And then you can access this either through Python, like in this example, to define some processing. Jeroen will show you much more about this, so I skip this. Maybe interesting is also the web editor. This is another client in openEO. I can quickly show you this also live. This is something which is based on JavaScript. Here you can connect through a backend, for example, the one in Eurac. There are different ways of authentication. For example, here we have a guest with the password guest123. And here you can get an idea about this, again, what is available in the backend, the processes, the data sets. On the left side, you can do some predefined processing here just for testing. For example, here we have a process graph now, so we can basically design this here then in a completely interactive way, the process. So you have all these things here. You can just basically drag and drop them in order to define how you do it. I now just use the predefined one in order to show you. You can select a data set that you want to run on. Then you can select your bounding box where you want to do your operations. Let's do something here close to where I'm sitting. So I'm sitting in this city right now. This is from here where I'm talking. We can run this over the whole time series, and we just need to adapt how these bands are called here. This processing chain here will compute enhanced vegetation index, or in short, EVI. And this is what's happening in this function here. So this is a reducer which has behind it the graph of calculating the NDVI. So there are different formulas to do that. And then since we have a time series, we want to reduce this and get only the minimum value for each pixel. And in the end, since we want to visualize the result quickly, we do have to do a stretching in order to arrive at something that is visualizable. And then we can just execute this and pray that it works. So it did. So here we can then see directly the result. So this again is the area that I have selected before. And you can see that this is the result as quickly and browsable. By clicking this button, this was a synchronous call, so it will get immediately executed, but you can also, as I said, if this now would have been run on a larger time series or a larger area, you could also add this graph as a batch job and then submit this for processing on a later run. This gets created here. And now it asks me if I want to queue this job for processing or not. I can do this now. Since this is still relatively fast, it's basically immediately finished. And then I can even download my result and have it as a file instead of having it just in my browser, basically. So this was this. Here's also some overview of Jeroen's, some overviews of the different backend implementations, but I guess I'm gonna skip this now due to time issues so that Jeroen also has enough time for presenting his stuff. As a summary, so openEO has defined a RESTful API. It's an interface which is human and machine readable in JSON. I showed you these short examples there. We have defined this catalog of processes, standardized basically, and these processes can be extended by user-defined functions so that you can do more complex things. We have standardized the process graph in an abstract way, so to describe EO computational workflows. So this process graph can be run on any different backend and is defined independently on what's running in the background, basically. We have a number of different reference implementations which are under development based on a lot of different programming languages, and you can get access to this through GitHub. All of this has been implemented in existing hard and software infrastructure, so the whole project has been designed from the way of being highly integratable in existing infrastructures. And since everything that we do is open source, this can also be a starting point for doing your own implementations, and you can have all the different documentation and guides that we already provide online. And if this is not enough, then you can also get in touch with us. So you have the website again. We have our mailing list here hosted by the TU Vienna. Oops, sorry. We have also our Git, which is very important. And yeah, all of our project documents are also online. So all our reports that we submit to the European Commission, once they're approved, you can find them on our Zenodo community. So we really try to be as open as possible in the whole workflow to be true to our name there. And of course, also acknowledgement to the European Commission for funding this under the grant agreement listed here. So with this, I am done, and I would give the word now to Jeroen and make him the presenter here.
Thank you, Alex.
I think, did it work? No, wait.
Probably not, because I'm still seeing your screen.
Yeah, let me see if I have to stop this here. In theory, I should be able to make presenter. Okay, now you should be there.
Okay.
Yes.
Do you see my screen then?
Yes, I see your screen.
Okay. Good. So this part of the webinar is the live demo. And here we focus, in fact, on the Python client. So what Alex just showed was how the web API works. But an important part of openEO is that we also want to be user-friendly to the end user. And the end user is usually like, in this case, for Python, we are targeting a researcher who doesn't even know about web services or JSON or anything, but he might know about languages such as Python or R. And that's why we created the Python client here. And we try to expose some of the openEO API, but also remain Pythonic so that user immediately feels comfortable with what he's doing. Also, the demo tries to show some of the main capabilities of openEO. Here we're using a phonology analysis example on top of Sentinel-2. And the part that we are showing here is actually the pre-processing, because Sentinel-2 is rather noisy data due to clouds. And even if you have the send-to-car scene classification available, which should tell you where the clouds are, you will still have a lot of noise left in your image. So this demo is about trying to reduce that, and we'll learn about some of openEO's features in the meantime. So of course, in a notebook, we start with some imports, and then it's time to connect to an openEO backend. You saw the different backends on the hub. You will find the URL there, and you can simply do openeo.connect. You can list collections if you want, and then you can load an image collection here. An image collection, it's a term that's also will be known to Google Earth engine users. It's basically a data cube. So you just specify the name of a layer, let's say. In this case, it's all of the data that the Terrascope, the Belgian collaborative ground segment, is hosting for Sentinel-2. And it's a level 2A product, so it has multiple bands. And we can also immediately filter on a bounding box if we want. Of course, if you're going to set up a viewing service, then you might even do a global layer. So then you don't filter. Then we go on, and the first thing we want to show is a computation of an enhanced vegetation index. And we use this example because it's slightly less trivial than an NDVI. It's not a very complex index, but it has a formula, and you see it actually here. So what you see is that we are using plain Python. We just select the bands of our data cube, and then we use plain Python math operations to write down our formula. And so that's how we hope to make things really usable and readable by researchers. Then here, to demonstrate what's going on in the back, we also show the graph or the process graph that will be sent to the backend. During normal usage, you will never want to look at this graph or show this graph, because what you see immediately is that the graph can become quite complex because you used a few operators here and there. And so as a user, you don't want to see this, and that's why we hide this all in the client implementation. So this will be sent to the backend, and then you can get some imagery. Like here. So you see that we can specify a date for which we want to download an image. We already specified the bounding box, and then we say simply download it as a geotiff, and we plot it on the client using regular raster.io plotting functions. So what you get is an image with some clouds already masked, but also at the edges of the clouds, some remaining undetected cloud, and the rest of the notebook will be about getting rid of that. So first we do some cloud masking. For that we use the scene classification layer, and we again use simple logical operators to select specific values out of these layers. So here we retain the vegetated and not vegetated pixels, and everything else we don't want. So basically, the mask is says where the clouds are in this case. And then we'll make it a little bit more fancy because we know that Send2Car doesn't detect all of the clouds. So we will use some kind of fuzzy logic here using a kernel to extend the mask a bit. So we will, at the edges of clouds, mask a few more pixels using this Gaussian kernel. And of course, we need a way to apply this kernel in openEO. So the matrix defining the kernel is here on the client side, but then we simply can send it to the backend using this apply kernel method, which will result in a mask which is no longer binary. And then we have to make it binary again, so we apply this threshold. So that's a parameter that we can set. What you have to know is that while we are doing this operation, we are specifying the operations. Nothing is happening on the backend, so we are simply building up our process graph on the client side. So it's basically kind of like a lazy evaluation that is happening here. So eventually we have our mask. And then we can again try to download some images. I printed some of the timings here, so you see that the longest one took 10 seconds. Just to show that all of this is happening on the fly. Of course, the images are not very large anyway in this case, but the point is that openEO the backends inside openEO are scalable. So for instance, ours runs on a Spark cluster, so the requests that you send as a user end up being run on a distributed processing cluster that is quite powerful. So that allows you to do these kind of synchronous requests that return in a number of seconds, which are really nice for exploratory research and doing trying out stuff and immediately getting feedback. So here you see our images, and you see in the middle that we indeed managed to mask a bit more data, and on the right you see the result of the mask before applying the threshold. So good, we've done that. In theory, actually, we could also create a viewing service. That's not yet something I can show in the live demo because I would need to open it here in QGIS, and it's not super fast yet. It's okay, but we want it to be better. Then we go on, and because we are doing time series analysis, of course, it makes sense to retrieve time series data. openEO has functions for that, so we can retrieve for a polygon the average of all pixels inside that polygon. We do that here. We can do it for the masked and the unmasked version. And then eventually we can plot it. Just let me see. Is it here? Yeah. So this is an example of how our time series looks like after applying the mask. You see that some noise is reduced, but there is still some spikes remaining which are not really normal. So it's if this is a potato field, for instance, and it's not normal that you have the spike and then it recovers. So that's probably still because of residual clouds or data that is not very clean. And this leads us to a final feature that we want to demo, which is the using of user-defined functions inside openEO. Because a common way to solve this problem is to apply a smoothing. And one smoothing algorithm that exists for that is called Savitsky-Golay. And if we apply it on the time series on the client side, we can get this result for, we have the original one in blue, and then the other two are in using different parameters. And you see that indeed we managed to smooth the result. But this was on an aggregated time series, so on the whole polygon. But it could be that we also want to do this on the pixel level, which would allow us, for instance, to really do some gap filling and to generate rasters that are clean, full complete rasters instead of doing it on the aggregated level. That's of course a heavy operation. That's one problem. And another problem is that this Savitsky-Golay method that we have here, it's not trivial. It's implemented in SciPy, and I just used it, but I don't know how it works at all. I can't implement it myself in terms of the predefined functions that openEO offers. That's also a limitation that other platforms, such as the Google Earth engine, have, for instance. You cannot simply run your own code. And that's what we try to solve also in openEO. So we allow running user code on the backend, so you can reuse all of this nice algorithms that, for instance, the Python community has already available in packages, popular packages like SciPy. So how does that go? We need to define a user-defined function first. And that's basically a Python script that looks like this. It has to follow a certain contract. It will receive a bunch of image data as input, and then you apply your function. So after some NumPy data mangling, you apply your Savitsky-Golay filter here, which is exactly the same as what I just did in the notebook, and you return the smoothed result. And in this case, the input will be a full time series of pixels, so for pixel data for multiple dates, so you can apply the Savitsky-Golay filter in time. And applying this is done using the apply dimension method. We are printing the documentation here, and here you see that we have our data cube, our masked data cube that we created earlier on, and we simply say apply dimension, and again now retrieve a polygon for that. So if we do that, we get a result. Let me see, we can retrieve a bunch of time series. And then we get this plot here. So you in green, you now see the result of, again, for a polygon, but now the Savitsky-Golay has been implemented on the server side on each pixel individually. That's nice in a time series, but the other nice thing to do is then to actually retrieve an image where that has been applied. So you saw the images in the beginning, which had some gaps due to clouds. And now what we did was doing a gap filling using Savitsky-Golay. So this is not raw data, this is reconstructed data that has been smoothed on the pixel level on the server side. And that is what we wanted, because that type of data is more suitable to do analysis on, because it's less noisy. And that's it basically for my demo. I think I covered everything. So I believe, Alex, that we can then go on to questions. Or
yeah, exactly. So thank you, Jeroen, for presenting this nicely. So yeah, from this point on, you are free to ask us questions to openEO, something that was not clear or you want to hear in more detail, if you want to have something on specific clients or backends or whatever, just let us know now.
So, hi, really nice webinar, thank you. So I'm Andre from Synergize. I have a couple of questions. So I really like this fact that you could apply this smoothing on the neighborhood, on the mask, so that you take into account neighborhood of pixels. But this is probably backend specific, right? So if backend allows you to do this.
No, actually, the apply kernel function is one of the predefined functions of openEO. It's one of the processes. So each backend that implements it should be able to do this. Yeah.
But the backend has to implement it, so it's not guaranteed that every backend implements it.
Yeah, that's a key point. So we have a list of predefined functions, but indeed the backends can advertise themselves whether they implement it or not. And that is why we are thinking of creating, like, let's say, a profile, like a minimal set of predefined functions that you at least should implement to be eligible to be a minimal backend, let's say. We list a couple of them now in the openEO hub, but in the end, there will probably be backends that implement enough predefined functions to be, let's say, compliant to this minimal profile. And other backends will not be compliant, or that are not compliant will be less interesting to use. So that's that way we want to solve this problem, because otherwise, indeed, the user would still have to part this code depending on only using the functions that a given backend supports.
Yeah.
Here you can see this again, what Jeroen just said. I think you should see my screen again now. And here on the hub, you can basically see what's available now in every backend, which functions and so on are there. And as he said, right now we are still not completely finalized with this, but we will come up with the standardized catalog profiles of functions, so that there will be a minimum overlap of what is available in all the backends. And after that, there's still the user-defined functions, which then basically give full flexibility. But of course, also there it depends on if a backend wants to have this level of flexibility for the clients to be done, because of course this comes also with some kind of security risks if you not have designed your backend well and sandbox it in a good way, basically.
Yeah. Okay. I have two more questions. So what is the limit on, or what is the restriction on user-defined functions? So I mean, here you used a method defined in SciPy. So, but probably you are limited by the, let's say, packages that you could use, or this is also free, up to the user to use whatever he wants.
For this, we currently envision the concept of having multiple runtimes available to the UDFs that can also be selected when a user launches his UDF. And also one of the ideas there is that runtimes can be Docker containers. So you could imagine that the user could run his, or also specify the Docker image name in which he wants his UDF to be executed. And then again, you have a lot of control over packages. But indeed, for now, that's what we do at VITO, and what is already working is a good list of predefined packages that are very commonly used, but that is indeed fixed, yes.
It's the same. We have not running it publicly yet, but also in our case, we have a predefined environment with a lot of typical libraries that people use in Earth observation. And of course, then it can be based on input of people who are using our infrastructure then in order to see what makes sense to put in there if essential things are missing. But then, as Jeroen said, you can just define a new environment as an option which has basically more power, or you could even envision that based on authentication you allow a trusted user also to install libraries in his environment basically on the fly or something like this, depending on how much you trust your users. But this is something, for example, if I would have a user group of my own colleagues in Eurac, then I could give them more rights than a random person that I don't know who it is, basically, in terms of what they can do.
Yeah. So yeah, I was thinking also ahead about the hackathon ideas. So one of them was also to execute S2 cloudless, so our cloud detection in openEO, and with this user-defined function, if we would be able to install all the necessary packages, probably the live GBM is the most critical one, and it's not probably part of your current stack. Then it should be, it looks quite easy to do.
Yeah, I think right now this could only be done with the guys from VITO as far as I'm aware. So maybe Jeroen can answer if they would be able until the hackathon to implement that in the environment.
Yes. So adding new packages is indeed something we can rather easily do, but it's best to arrange that indeed before the hackathon, because indeed it can take up to a day to roll out something like that. Depending also on the complexity of packages that need to be installed as well.
Okay.
So the best would be that you send us an email with the exact requirements to Jeroen, and then this should be okay.
Yep.
Okay. And last question. So thinking as a developer, so when you develop or try new stuff, you don't get always correct in the first attempt, so you have to debug. And here all the executions are done on this backend side, right? So not on the client side. So how do you then envision this? So how can users debug stuff, and can it be executed also locally? So fetching data and then process it locally?
Yeah, that's a good point. And we've been thinking about it. One way is of course giving insight into what is happening on the backend by exposing certain external views. Let's say that's one thing, but even then you would not be debugging at the level of the programming language. So what I have been thinking there is that indeed it would not be hard to foresee a process that downloads a part of a data cube, so a small bit, and that you can then indeed run your code locally on it. Especially, for instance, for helping out with user-defined functions, there it's fairly relevant. It would be really nice that you could ask the backend for a data cube that represents the data that goes into the UDF. You download it locally. It would not be too hard for the Python client to then run the UDF locally on that data set and show the result. And at least that would allow debugging of the UDF. For the other predefined functions, there it is slightly more difficult, of course, because then you need a Python client-side implementation of all those things. Although that, yeah, it might be feasible, because, like, for instance, there is also the R backend, which exactly does this, so implementing a number of predefined functions in R. And a similar thing could be done with Python, where you have certainly enough libraries available to do this. But that would still need to be done. But my first focus is actually on the UDF ID there. But it won't be there for the hackathon.
I mean, the rest of all the messaging happens over the different error codes that come basically defined in the interface. So if there's happening something on the server side, you would just get a 500 something error, which should tell you in a meaningful way what went wrong. This, of course, depends on the implementer of the backend, how detailed this information is. But yeah, we were thinking also of having some kind of mechanism of propagate, some kind of error stack to the client as well.
Okay, thank you.
Yeah, we still have around 10 minutes, so don't be shy and ask more questions if you want to, both from the attendees and also from the other presenters, if there's something that you're curious about to get more insight on.
Yes, Alex, Jeroen, thank you very much for your presentation. This is Jose from Candela. One thing, this is something that we are still pending to do among the different projects that will bring their tools to the hackathon, which is specifying the technical requirements for the people attending the hackathon in order to be able to test the different tools. So yeah, can you already anticipate a little bit what you will expect, or what will be the needs of someone that should bring in advance on their PC, on their laptop, in order to play with openEO API and the different tools.
Okay.
I know we still have to define that, and will depend very much also on the predefined exercises among the different projects, but maybe this will help also to the attendees to have an idea on that.
In this case, I think for openEO, the easiest is to start looking into what you are actually interested in doing. Are you somebody who wants to work on backend related questions or client related questions? And then also thinking about how is your environment set up? Are you somebody who is interested in Python, R, or JavaScript on the client side, or on the back end? Am I already working with Spark? Maybe it's interesting to look into the GeoPySpark driver. Do I have a Rasterman data cube or any other WCPS based system? Then I can look into how this is done in the WCPS driver. And I want to develop an extension on the R client, then I can look here. In all of the cases on our GitHub, so GitHub openEO, you can find basically in the README documents information about what is needed. So all of them should have something that gives you information on the setup of the service and the operation environment. And that is basically, it cannot be done in a holistic approach that this is what you need for all of openEO, because it's so diverse. There's so many different implementations. But getting an idea of what you want to look into, then you can start looking here exactly. For example, this driver is based on Java 8, and then, as I showed also in the slides, you will need to set up an environment where you can run a web archive, which could be done, for example, with, I personally use Eclipse for my development, and then I can define a Tomcat server in my Eclipse and just test it all locally there, and I have my own development environment set up like this. And I guess for Python developers, it's similar. Somebody who maybe just from the client side wants to test something out with Python, then all you need is basically a simple tool like Spider or PyCharm or just a Jupyter Web Service, and do the development there.
And try running then pip install openEO. That should do it.
Exactly. We have made it available as a pip package, so then it's also easy to test that. I cannot show you my own Python environment right now because this is on a different secured network, which I'm not connected to right now, but that's indeed as simple as this, basically. And yeah, for the backend, it really depends on the infrastructure, and the different ones are set up very differently. I showed this earlier. I jumped over this during the presentation, but you can basically look into these documents and see what is the software stack in the different backends. Here's the example from VITO with their PySpark based backend. All of this, I think, I don't know, do we have this already available, the Docker environment of running this, Jeroen, for example?
No, that's something we discussed to provide it or to do that, but we haven't been able to do it yet. No.
Because this is also one of the plans that we, since in all cases the implementations are only software stacks. So all what you need to do is basically to run them, and you can also do this on your desktop. So also in the case of our Eurac backend, all you would need to do is basically have a Rasterman community server running locally, and then have an Eclipse where you develop with your Tomcat and deploy your web archive, and just make sure that this points to your local host of your Rasterman, for example. And I guess for Jeroen's VITO backend, it is very similar, and for others as well. I know that also the guys from EODC have a simple version of their cluster running in a local environment where they spin up the Docker containers all that they base their processing workflows on locally. But it really, you should look into the different ones, see what is closest to your setup, and then try to run this. This is the example of GraphJS from Actinia, from Mundialis, based on Actinia, and yeah. I guess that's it. There's also a simple version where you just basically host your own service, which then connects to the Google Earth engine in the background, developed by the University of Münster. Also, this is basically can be run as a local application, and then just forward your requests to the engine based on your Google ID, basically. Yeah. Does this answer the question a bit?
Yeah, for sure. I think so. Thank you very much.
Okay.